Good evening, all. Shall I start the session?
Yes, sir.
Please make me my mood. I am Pramod Gaval, research scholar, stay at this course. So I am going to take a problem solving session 12 on a chemical reaction engineering 1 course, week 12, non-ideal reactor designs. The course tutor is Professor Vishwanath Mandal's Chemical Engineering Department, IIT Guwahati. So I hope you have gone through the week 12 lectures which are available on some portals. So based on that, I'm going to take some MCQ and some numerical problems. So starting from the MCQ one, so question one: the vessel dispersion number for an ideal CSTR is. Uh, the dispersion number defined as D by UL. This is a dispersion numbers. So for an ideal CSTR, D by UL is a infinity. And for PFR, it is 0. So here as in the question asked for the ideal CSTR. So let's D. Moving to the question number 2. For an ideal plug flow reactor, the value of Peclet number is. Generally, Peclet number is defined as the reciprocal of the dispersion numbers. Like P, the Peclet numbers, it's a reciprocal of dispersion numbers. D by mu equal to D, right? So we know the popular flow that D by 0 or CFR. So, so it's going to become a infinity, right? Take less number infinity for ideal PFR. Right. Now moving to the question number 3, that the dispersion models accounts for. Option are given: a deviation from the ideal PFR, B a modeling ideal CSTR, C combining batch and CSTR, CSTR connected in parallel. So dispersion model involve a modification of the ideal PFR. It imposes axial dispersion on a plug flow. Option A is correct. So dispersion model accounts for the deviation from a ideal PFR. Now question number 4, this is numericals. The C curves measures during a pulse tracer experiment is shown in below. In the figure, CT is the concentrations upper tracer measures at the reactor exists in mole per liter at a time t seconds. So this is the graph given CT versus time. The mean resident times in the reactor rounded to the one decimal places. So you have to calculate the mean resident time. So using these graphs. Right. So mean resident times. Right. Denoted by Tm. Right. So Tm equal to 0 to infinity T dt, dt, 0 to infinity, t to dt equal to 0 to infinity, t, t, t dt. Right. This is equation 1. And t, t equal to t, t. Here, based on the data given ct, so we can write out here ct 0 to infinity, t, this is the equation 2. Now, the area under the curve, this ones, these triangles, area, am I audible?
Yes, sir.
0 to infinity, c, dt. So this is the area under the curve, this one portions. Now to calculate the area under curve, 0 to infinity, c, c, dt equal to 0 to 2. Here per time 0 to 2, 0 to 2, dt, dt, right, is equal to area under the curve. So area of these triangles, 1 by 2 into 2 minus 0, this is base, this is the height. Right? So 2 minus 0 into 1 minus 0. Right. So it's a 1. Right. So 0 to infinity c t dt equal to 1. Now combine equation 1, combining equation 1 and 2. Tm equal to 0 to infinity t t t dt 0 to infinity t t t dt. Right. So we can write down Tm equal to this one 0 to 1 and 1 to 2. 0 to 1 T T dt plus 1 to 2. Now 1 to 2 T T T dt. Right. This is equation 3. Now to calculate this part, so here is the triangles. Its value here 0 0. Here 1 1 x y. Here is a 2 0. Right. So to calculate this part, like t 0 to 1 t 0 to 1. So from this point, we have calculate the slope. Y is equal to, sorry, mx plus c. Right. So m 1 minus 0, sorry, 1 minus 0 is equal to 1 slope. And intercept of this line is 0. Put means any value in this equation, you will get c is equal to 0. Right. So c y is equal to m. It means ct equal to y is equal to x. Ct is equal to t. Here is a t x axis. So here t. Now for second part, from the time t 1 to 2. So y is equal to mx plus c. So calculate the first from these lines. So slope is minus 1, and take any point and calculate the slope. So slope is c is equal to 2. Right. So y equal to minus x plus 2. So based on this data, ct equal to minus t, right? Minus t plus 2. Right? So we can write down 2 minus t. Right? Now put this value in this equations. Equation 3. So tm 0 to 1 t, right? dt plus 1 to 2 t 2 minus t to dt. Now integrate these equations. 0 to 1 t square dt plus 1 to 2 2t minus t square dt. Right. Tm equal to with limit 0 to 1 plus 2 t square by 2 minus t cube 1. Right. So Tm equal to, put the value here by 3 plus 2 2 square minus 1 square minus 1 by 3 2 cube minus 1 cube. Right. So Tm is equal to 1 second. This is the mean residence time in the reactors. So this is the one approach. Now in second approach, simple one. So here t, the mean residence times is a x coordinate of the centroid of a triangular distribution. So t equal to is 0, 1 and 2 plus 1 plus 2 divided by 3. So 1 second. All of you got clear?
Yes, sir.
Moving to the question number 5. An isothermal pulse test is conducted on a reactor on TTO variation of the outlet pressure concentration with the time is shown below. So pressure concentration time graph given. And the mean resident times of the fluid in the reactor in a minute. So you have to calculate here mean resident times. So here time versus pressure concentration graph. So these conditions like T1 is equal to 5 minutes. Add this and C1 is equal to 20 minutes. 5 minutes. C1 is equal to 10 mole per and delta T1 difference between these points is a 5, right? Similarly for this point T2 equal to 10 minutes, right? And C2 equal to 10 mole per liter and delta T2 equal to 5 minute, right? Now to calculate the mean resident times, the formula is T equal to summation of Pi Ci delta Ti divided by summation Ci delta Ti. Into here T1 T1 delta T1 plus T2 T2 delta T2 divided by C1 delta T1 plus C2 delta T2. So all the value we have, so put in this equation and calculate the mean resident times. So 5 into 10 into 5 plus 10 into 10 into 5, right? 10 into 5 plus 10 into 5. So T equal to 7.5 minute. Right. Option B is match. Allah to got clear.
Yes, sir.
Okay. Moving to the question number 6. A CSTR has a long inlet pipe. A tracer is injected at the entrance of the pipe. The E curve obtained at the exit of the CSTR is shown below. The graph gives ET versus time. Assuming plug flow in the inlet pipe, here assumption given plug flow pipe in the inlet pipe, the ratio rounded up the second decimal place of the volume of the pipe to that CSTR is. So here we have to calculate V pipe versus V CSTR. So you have to calculate this, right? So here 1 by T 1 by T CSTR into this is the 0.05, right? And T equal to 1 by 0.058 at 20 the resistance times. This is where the CSTR initially assuming the PFR. So T for T, this one T PFR equal to 5 minutes, right? They given. So here in the question that this is a long pipe considered as a PFR flow. Right? Then CSTR, CSTR, a long pipe and plug flow here. Right. So T PFR is 5 minutes and T CSTR is 20 minutes. Right. Now P pipe divided by A equal to 5 minutes. Right. That's the times precedent times. Here VCSTR divided by F equal to 20. Right. Now we have to calculate V pipe divided by VCSTR. V pipe VCSTR value is a 5 20 years. Right. So 0.25. Ratio is 0.25. Now moving to the question number 7. A liquid is flowing through the reactor at a constant flow rate. A step input of pressure at a molar flow rate is 1 mole per minute is given to the reactor at a time t is equal to 0. The time variation of the concentration C of pressure at the exit of the reactor is shown in below. Okay, here is a graph given concentration versus time. Okay, and there's changing behaviors here given. So first we have to calculate the volumetric flow rate of the liquid through the reactor in liter per minute. The second one, the mean resident times of the fluid in the reactor in a minute. So here this is a maximum. This is a maximum concentration. This was so C max equal to M by B. Right here, C max equal to 1 mole per liter, and here is the flow. Here M is a molar flow rate given 1 mole per minute. Right now, calculate the volumetric flow rate equal to m by c max, right? So put the value here, moving per minute in liter per, so it cancels the 1 liter per minute. Option is correct. Now we say B part, the mean reaction times of the fluid in the reactors in minutes. So to calculate the mean reaction times, so T max, sorry, into C max equal to shaded area, right? So this one's so mean the resident times of fluid in the reactors. So to calculate the shaded area, first is this is a rectangular, then minus this of this first is the area of rectangulars, 1 minus 0 into 5 minus 0, then minus, sorry, this is not a minus 1 by 2 into 5 minus 1, this is a base, and height is a 1 into 1, right? This one shaded area, 2 5 minus 2 to 3, right? So T into shaded area divided by senior, 3 by 1, no 3. Option C. So I cover all the question based on the 12 chapters. So if you have any doubt, please ask because today is the last sessions of this course.
No
If you have,
doubt, sir.
if you don't,
Thank you.
if you have don't doubt, I'm going to conclude the today sessions of this course and best of luck for the final exams. Thank you. Good evening, all.